Yep.
For our bio project, we're doing MMA.
Yep.
We decided to do 3 different fighting styles.
Okay.
Just 3 of us would each have separate fighting styles.
Sure.
It's cool if we do each do like 3 mini intros for each fighting style.
Sure.
Related to bio.
Yeah. No, I think that'd be great.
Okay. Yeah, I was kind of concerned like we do like all together as well, or 3 separate.
Yeah, I think it's okay.
3 separate, like why they're each related to bio.
Yeah. No, I think that'd be good.
Going for your axis or 410. What is a simple model?
Yeah, so the simplified model, that's like basically just any kind of hand calculation that you're going to do to verify your results.
Okay.
So I don't want you guys just to use finite elements, just ANSYS. I want you guys to be checking against something else. And so basically any kind of calculation that's not ANSYS will work for a simplified model.
All right.
Yeah.
So I'm doing the same thing for senior design. Am I able to use the same? I'm using senior design for the components. For your answer class, I'm using what's the final.
Nice.
I'm able to kind of add on or use the same thing. For yours, obviously, I'm adding more detail.
Yeah. No, that's perfect. Yep.
Because both he does require hand calculations and simulation.
I see. Yeah, go ahead and do the same thing. Yeah, that way you can get my feedback on it too, and then because it's part of the 410 project, and then there's some synergy between those classes.
Okay.
Yeah, Dr. Lee and I talk all the time, so yeah, we wanted it to be like this, where there's like you guys can kind of use the same, analyze the same things for both senior design and also for finite elements. Yep.
question. For
Mhm.
analysis of your project,
Mhm.
would you have to do like pseudo like mathematical analysis or just like a quick explanation of what, let's say movement uses this hamstring to pull this muscle or this
I
something
would
like this?
I would like to see some numbers on it. So like
Okay.
basically like the examples that we do in class or
So
like on the
like
exam.
assume like the weight and then assume how much force
Exactly.
they're gonna exert.
You can plug in as long as the numbers are reasonable.
Reasonable, yeah.
As long like they don't have to be like perfectly pinpoint
Okay.
accurate, but it's like as long as they seem reasonable, just so you can get a sense. Like especially if you're comparing like different moves.
Uh-huh.
And so I want to see how much more taxing would sort of be on like the hips or something like that versus
Okay.
like versus another move.
Okay.
And so I think that's kind of the point of those kind of calculations.
All right, all right. Yeah, it's my team needs to kind of use it. Do we just do something like this and
Mhm.
describe, or do we use numbers?
Yeah, I would use numbers. So that looks like a great free body diagram already. You just have to plug some numbers.
Okay, this is just like for the homework. But yeah.
Okay.
I'll do the same thing
Mhm.
with numbers this time.
Yeah. Mhm. Hey, Samson. It was good. Yeah, I saw some family that I haven't seen since before the pandemic. So that was nice, but also stressful in a way because family gatherings can be stressful with a lot of people that have a lot to say about your life. But you know how it is. But besides that, it was really nice. How was yours? Oh, you got new beds. Oh, so you're breaking them in. Ah. Oh, I see. I see. Well, hope you recovered. Hmm. So how that Thanksgiving hangover? Too much brunch. Nice. That sounds good. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How is everyone doing? It's been a while since we've seen each other. How was everyone's break? Good, good. Yeah, it's been a while, right? So we're in the last 2 weeks, and so we have lectures this week. So I have something planned for today and on Wednesday, and then starting next week, we're going to start our final presentations. Okay. So later this week, I'm going to put out a sign up sheet for you to sign up for a presentation day and time. Okay. So what I'm thinking is I think we have about like 8 or 9 groups. And so I think that's the perfect number. And so I think we'll have half people go on Monday and half people go on Wednesday. About 4 or 5 groups we will go per day. And so that gives time for about a 15-minute presentation per group, which I think will be really nice. Okay. So I'll be putting out that sign up sheet later this week. So make sure, make sure you're aware of that. Okay. Okay. And so the topic for this week, which is going to be our last big topic of the class, is balance. Okay. And so, we talked a lot about in this class about, stresses on, muscles and on bones and on joints, right? As a result of static formations or dynamics. And so, I want to do something a little bit more specialized at the end, talking about how the body keeps balance and, how the body can kind of maintain that. Okay. And so today we'll do what I like to think is kind of like the computation part of this unit, where we'll define quantitatively what it means for the body to have balance, and do some computations on determining whether certain body states are in balance or not. Okay. And then on Wednesday we'll talk about what are some more qualitative topics, like what does your body actually do to help maintain balance. Okay. And I wanted to cover this one early today because some of the computations that we do today I think will be also good candidates for your final project as well. Okay. And I just want to clarify, on the final project, I actually do want you guys to do some computations. Okay. So I want more than just free body diagrams and just descriptions of what's going to be of what's going on in your project topic, but I want you guys to actually plug in some numbers to them there, to give a sense of how much stress is your joints undergoing, how much work are your muscles doing. Okay. And, and so we've done basically two big units up to this point, one on statics and one on dynamics. Okay, so both of those would be great for a lot of your projects. But balance is also a pretty important topic as well, especially for some of your topics that require it. So a lot of your sports, a lot of people who are doing sports biomechanics, balance is a really important thing for those as well. Okay, and so you can use some of the techniques that we go over today to help you out with your project. No, so we're doing final presentations next week. And so basically the final lecture week is going to be on final presentations. Okay. I don't like to do final presentations during finals week. First of all, because I know you guys have other final exams you guys are worried about, but also because I want you guys to come and watch each other's final presentations as well. And that's the main reason why I'm having it for this class. Because there's so many really cool and interesting topics in biomechanics, and I want you to basically learn from each other. And so, we'll have it during the lecture times next week, so you guys could all get a chance to share. Yeah. So during the actual final exam week or final exam time, we don't really have anything. But the report is going to be due on December 20th. Yeah. Yep. So next week will be final presentations. The next week, finals week, we have nothing due, and then the Monday after finals week, that's when the final report is going to be due. Yeah. Mm-hmm. All right, and so I think that's all the announcements. Oh, homework 6, which is the dynamics homework, that was I put that up before Thanksgiving, and that's going to be due next Friday. And again, that's going to be optional, and so that the only people that have to do that are the graduate students in this class, and that's the extra assignment that you have to do to have this count as graduate credit. Okay, but if you do want to do it, then I'll give you extra credit for it. It'll be about half of homework assignments worth of extra credit, and that goes for the graduate students too. Okay.
It's not due on the 20th. It's due next Friday. What's next Friday?
Next Friday would be, let me see, something like that. Oh, not, it's a bit sooner than that. Next Friday would be the, I think would be like it would be the 10th, I think, something like that. Yeah. Mm-hmm. Okay, so I think that's all my announcements. So are there any questions I can answer before we get started?
So I have a question about the presentation.
Yep.
Like for mine, there's a lot to explain.
Mm-hmm.
For example, like even amongst even though there's only 3 lifts, there's a lot to explain.
Yep.
So is it okay if for the presentation we hone in and get very specific about the biomechanics of one aspect of our project? Is that all right?
Yeah, I think I would prefer that as well. Okay. And so if you look at the requirements for the presentation, it doesn't cover everything that's in the report. And in particular, I want 2 biomechanical analyses in the presentation. And so something with the numbers. So either 2 static analyses or 1 static, 1 dynamic, maybe 1 static, 1 balance type of calculation. Okay. And so you can focus that on just one motion in your project.
Okay, cool. Yeah, because I read that it didn't have to be super specific, but I didn't know if you wanted a general overview or if it didn't have to be a finished project. Mm-hmm. So I just didn't know if we could completely hone in on one aspect of the project. Yeah,
I think that's totally fine. Totally cool. Yeah. I mean, I'll leave it up to you guys, but that's totally fine. Okay. Yeah. 15 minutes. It might sound like a lot, but it's actually not that much time, especially if you're going to cover a whole report's worth of information. So you can choose what you want, but make sure that it's a good amount of information that that people that can watch your presentation will come away with something. Okay. Remember, so the only other person that's probably going to be reading your report is going to be me, and so I don't think anyone else in the class will read your report. And so make sure the presentation is kind of good on its own, so that people, your peers can watch the presentation and come away with something valuable. Okay. All right, and so let's get into the lecture today. Okay. All right, so the topic for this week is going to be biomechanics of balance. All right. And so, keeping balance is something that our bodies do, all the time, right? You stand up, you sit down, your body has to maintain balance. And we don't really think about it a lot, but the body actually has to do a pretty decent amount of work to keep balance. Okay. Okay. But even though we don't really think about it, a lot of it's still, it's still a responsibility. And the ones that usually maintain this the most is your muscles. Okay. Okay. And so, if you've ever had a job, or if you've ever done something where you had to stand up for a long period of time, like you'll notice that you get tired, right? And so keeping balance is it's not trivial. So your body's actually working. And usually you don't really notice until you kind of get tired. Okay. So let's define some definitions to help get the discussion started. Okay. And so let's start with a definition called the base of support. Okay. And so the base of support is defined as the area beneath the person that includes every point of contact the person makes with the ground. Okay. And so you have a regular person just kind of standing up like this. Okay. Standing up on the ground. If we kind of just took a zoomed in view of his feet, and we kind of look from above, it might look something like this, right? So you might have one foot that's like this, another foot that's like this. Okay. You have some weird looking feet, I know, but it's the best I can do. And so the base of support would basically be if you drew a box around the foot. Okay. And so basically the idea with base of support is that you take, for most of us, it's going to be our feet, right? So you take your feet and kind of drew the smallest box around both of the feet as possible. That's going to be your base of support. Okay. And so depending on how big your feet are or what position that they're in, right? If you have them closer together or if you have them farther apart, then that's going to make your base of support either smaller or bigger. Okay. Right. And so this is important because if you draw kind of a free body diagram of this person just by itself, right? We have basically two forces, right? And so on the one hand, we have the person's weight, right? Right. And so if we define the weight to be acting at the person's center of mass, okay, and so that's going to be acting downwards. And then in order to maintain linear static equilibrium, there has to be an equal and opposite normal force that comes from the ground, right? Because the net forces on this person's body have to be zero because they're just standing still. Okay. But the way that we draw these normal forces, and so we'll call this N1 and N2, okay. These are always going to be to act through our feet or through our base of support, okay? And so if I could draw them here, as an approximation, N1 and N2 would be acting on the edges of our base of support, okay? if we want to match up with that diagonal. Okay. And so if you if we took this this image here, okay, and let's say if we were to sum the moments, okay, and let's sum the moments around a point right here, so we'll call this P, okay, right, and so P was directly below a person's center of mass. And if N1 and N2 are the same, so let's say that, you know, this person's standing up completely normally, so both feet are basically, you know, supporting the same amount of weight, then we can see that the net moment around this P is 0. Okay, because the person's weight is acting directly towards into that pivot, and so the weight is not going to have any contribution to the moment. Okay, and because N1 and N2 are equal, then the net moment around this point is 0. Okay, and so in this situation where there's no rotation of the body, or there's no net torque on the body, we say that this person is totally balanced. Okay. All right. Any questions on this so far? Okay. All right. And so let's break apart this the situation here where we have balance, and let's pick apart kind of the most distinguishing features. Okay. And so in other words, what we can say is that a person is balanced, or they're not going to start toppling over, basically if the center of mass or the center of gravity stays within the base of support. Okay. Right. And so imagine if as your base of support is being kind of like almost like a light beam or like a force field around it, okay? And so if you can right now, if you can stand up and imagine that there's kind of a light sheath that goes from your feet up around your body, okay? As long as you keep your center of mass within that sheath, then you're going to keep balance. And so visually it looks something like this. We have a person, okay? Let's say that he's adopting a pretty wide stance, okay? Let me draw the ground. Right, and so if we take the base of support and then extend it upwards around the person's body like this, okay, right, and so that's kind of like a force field around the person. As long as this person keeps the center of mass within this force field, then he's gonna keep balance. Okay, right, and so he can even do stuff like, let's say that he starts to bend over, okay, or bend to the side. So let's say he starts to kind of do some calisthenics or stretches like that. Okay. Let me draw the base of support here. Okay. Right, and so even though he's kind of bending to the side, and so of course that's going to shift his center of gravity over that way. Okay. He's still going to stay balanced because that's all within his, within that base of support. Okay. Because if we do the same calculation here, so let's say that we make a point P, okay, right? And if we sum the moments around P, right, it's still going to be 0 because what you have here is you have the normal forces from the ground. So let's say you have N1 and N2, okay? And let's say that we have W. Right? So even though W here is no longer acting in towards the point, what your body can do and what it does is that it shifts the magnitudes of N1 and N2 such that you have no net rotation, okay? Okay. And so if you shift over to the side like this, N2 would probably grow in magnitude because you're shifting more of your weight towards that foot on this side, right? And because N2 is growing in magnitude, it can provide an opposing torque, right? Because if we take some of the moments around P, right, W and N2 are creating torques in the opposite direction, right? So W is providing a clockwise torque, where N2 is providing a counterclockwise torque, okay? And so since it's still possible for these two to act in opposite, then your body can adjust to maintain balance, okay? It might take some extra work from the muscles in order to do so, in order to shift your weights, but theoretically it's still possible in order to keep balance, okay? And of course, there are things that you can do to kind of help keep your balance, right? And so if you spread your legs out more, or you adopt kind of a slanted stance, and so if you've ever taken any kind of martial arts before, or if you do any kind of weightlifting, you know that in order to have better balance, you know that you should spread out your legs, and maybe have one foot in front of the other, right? And the whole idea with that is to widen your base of support to make it, to make it harder for your center of gravity to shift outside of there. Okay. All right. Any questions on this? Okay. All right. So what happens when you start to lose balance? Okay. And so you will start to lose balance when your center of gravity falls outside your base of support. Okay. And the reason this happens is because there's going to be no longer any kind of way for the normal force to counteract the rotation from the body weight. Okay. And so visually, it looks something like this. So let's say that, and I'm going to exaggerate this just to make it a little bit easier. Okay. So let's say that this person is kind of, very flexible and he can bend over like that. Okay. And as he's bending over to an extent such that, if you define the base of support like this, then his center of mass, might be somewhere over here. Okay. Right. And then just like before, we have N1 and then N2. Okay. All right. And so normally, when the weight is within your base of support, then N1 and N2 can provide counteracting torques to prevent any kind of rotation. Okay. But now let's look at this situation. And so let's say now, let's sum up the moments around here. We'll call this P, okay? Right? And the reason I chose this point is because, if you're tipping over to the right, okay, like this guy is, then you're going to be rotating on the foot that's kind of planted on that side, okay? And so so basically by performing this calculation, we're looking to see if the body's going to rotate around that fixed point, okay? All right. And so let's go look at the two contributions to this moment and see, what directions that they're in, okay? Well, first of all, let's look at N2, right? So because N2 is acting right at the pivot, and it's not going to contribute to the moment at all, okay? Right. So now let's look at the contribution from N1, okay? And N1 you can see is pointed upwards, okay? And if we draw kind of a line like this, we can see that it's going to produce a clockwise moment, okay? And to that, we're going to add the contribution from the weight. And you can see here that now that the weight is on the right side of your foot, outside of the base of support, it's also going to be contributing a clockwise moment. Okay. Right. And so when you have two torques like this that are providing moments in the same direction, there's no way for them to counteract each other. Okay. And so what's going to happen in this situation is that the body's going to start rotating clockwise, and its angular acceleration or angular velocity is going to increase until this person basically just smashes his head on the ground. Okay. Okay. Right, and it can happen very quickly too. And so basically only a couple seconds, or or maybe even like less than 1 second after your center of mass goes outside your base of support, you're going to find yourself rotating and toppling over. Okay, and so the name of the game, and so the whole game with keeping balance in your body is trying to keep your center of mass within your base of support. Okay. And so, there's the conscious things that you can do where you can kind of increase your base of support. You can spread your legs out or put them in front of the other. Okay. But there's a lot of unconscious things as well that your body's doing to make sure that this doesn't happen. Right. And so if you look at your abdominal muscles, right, and so your abdominal muscles are acting on your hip, right, and they're kind of responsible for the position of your torso, right. And so in order to prevent this from happening, your abdominal muscles is going to want to pull your body this way, right? And so they kind of attach kind of near your chest, okay? And then their other attachments on the hip. And so, subconsciously, to kind of prevent you from tilting over to the right, your muscles are acting to kind of keep your center of gravity, within this base of support, okay? And that's happening constantly. And so even without you really thinking about it, so even me just standing up here talking to you, I might subconsciously kind of sway one side to the other, but the thing that keeps me standing upright is my muscles, okay? Mostly in your core. All right. Any questions on this? Okay. Okay. And so there's two directions mainly where you can lose your balance, okay? Or I'd say two different ways that your center of gravity can go outside your base of support. And so the first direction is either from your front or your back, okay? And so that's one distinction. And the other way is side to side, basically, so left and right. Okay. Okay. And so the reason I'm making this distinction is that it's, generally it's a bit easier to maintain balance in one of these directions. And the responsibility of keeping balance in these directions is different. And what I mean by that, there are different muscle groups or different, muscles in your body that maintain balance in each of these directions. Okay? So generally speaking, just by kind of the normal resting stance that people usually take, it's generally easier to maintain balance in your left or right direction, because most people kind of, naturally kind of spread their legs out kind of shoulder width. And so because of that, you have a wider base of support in that direction. Okay. And I say that it's usually easier to do this, just kind of based on kind of the resting stance of a person. Of course, you can take a stance where you put one foot in front of the other, okay? And so in that case, you have much more stability in the front and back direction, right? And so some martial arts stance take that approach, okay? But generally speaking, left and right is a little bit easier, okay? All right. And one other thing that you can do to help you maintain balance is to lower your center of mass. Okay. And that's generally what you're told too, right? And so for a lot of cases, what they tell us is if you keep your center of mass lower to the ground, you're going to have a lot more stability. Okay. And the reason for this is that the lower your center of mass is to the ground, the more your body has to rotate in order to get the center of mass outside your base of support. Okay. And the height of the center of mass actually, it plays a big role. And so in the next two examples, we'll see, how much more or how much easier it is to lose your balance when your center of mass is higher. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do an example to kind of illustrate, or kind of put some numbers to this to kind of show you, what it's actually like. All right, so let's consider a case where a person is in a relatively wide stance. Okay. And his stance is wide enough such that he has about half a meter in between his 2 feet. Okay. Oh, wow. All right, and so let's say that he's standing up like this, okay? And the distance between his feet, let's say that this is 0.5 meters. Okay. Right. In addition, let's say that this person has a certain amount of height such that his center of mass is about 0.8 meters off the ground. Let me go ahead and draw his center of mass. Okay. And let's say that this distance right here is 0.8 meters. Okay. All right. And so for this problem, we're going to compute how much the body can rotate before he starts to lose his balance. Okay. And so basically we're interested in a situation where, let's say that the person starts to bend over. Okay. And let's say that the amount he's bending over is theta. Okay. Right. And so he's kind of leaning to the right a little bit. Okay. Or I guess it'd be his left and our right. Okay. And so we want to compute what this angle theta is. Okay. All right. Any questions on the example setup? Okay. All right. And so let's go back to our definition of what it means to keep balance, right? And so what we said was, as long as the center of mass is within kind of this imaginary cone, within our base of support, then we're going to keep balance. Okay. And so if we draw, our imaginary cone like that, okay, as long as the center of mass stays within that cone, then we're good. Okay. And so the kind of the limit of this, is the situation which we have there, where the person's center of mass is basically right at the edge of this cone. Okay. Right. And so let's go ahead and draw a triangle that kind of illustrates this this geometry. Okay. And so if we draw a triangle that looks like this, right? And so one edge of the triangle will be kind of the vertical height that the center of mass is off the ground. Okay. The horizontal distance will be around there. Okay. And so it'll be about half the base of support. Okay. I drew it kind of weird. Okay. And then the hypotenuse will connect those two. Okay. And based on the trigonometry of the situation, we can say that this angle here is the same angle theta that the person is rotating with. Okay, because we basically have two parallel lines, right? And so we have a parallel line for this one, and we have a parallel line for the edge of our base support. And so because this angle on one side is theta, if we look at the opposite angle, that should also be theta. Okay. And so let's take this triangle here and kind of make it a bit bigger. Okay. Okay. And so this angle right here is theta. Okay. We're going to assume that this person, as this person is rotating, his center of mass kind of stays the same height off the ground. Okay. And so the height of this triangle here is 0.8 meters. Okay. And then the horizontal distance, or this distance down here, because we define this line right here to be acting at the midline. Okay. This horizontal distance down here is only going to be half the width of the base of support. Okay. Because remember, the base of support goes from one foot to the other foot. Okay. But the midline is going to go right in the middle of that. Okay? And so the horizontal distance here is going to be 0.25 meters. Okay. And so based on this geometry, we can use this to solve for theta, right? Because what we have here is a right triangle, okay? And we have a given angle theta, and we have the length of the triangle opposite of that angle, and we have the length of the triangle on the adjacent side, okay? And so what we can say is that tangent of theta, okay, if we go by SOHCAHTOA rules, okay, tangent of theta is going to be the length of the opposite face. And so the opposite face here is 0.25 meters, okay, divided by the length of the adjacent face, which is 0.8 meters. Okay. And so we have tangent theta is equal to 0.25 divided by 0.8, okay? What we can do now is we can take the arctangent of both sides, or in other words, the tan inverse, okay? And then we can use that expression to solve for theta. Okay? And so you can easily kind of plug that into your calculator and solve, which I'll do on the next page, just because I'm a bit out of room here. Okay. All right. Any questions on how we got these numbers here? Okay. All right. So let's go ahead and evaluate this expression so that we can solve for theta. Okay. All right, and so if we say theta is equal to tan inverse or arctan, depending on your preference. Okay, theta is going to be equal to tan inverse of 0.25 meters divided by 0.8 meters. Okay, and we punch that into the calculator, and what we get is 17.35 degrees. Okay. And so under normal circumstance, this person can rotate about 17.5 degrees before, before he starts to lose balance. Okay. Can I go back to the last slide? Yes, I can. Mm-hmm. Let me go ahead and write the final answer here, just so, just for that's on the next page. Mm-hmm. Right. And so the result of this calculation here is 17.5 degrees. Are the two angles are equal? Yes, the two angles are equal. And so this angle here is same as the angle in this triangle. Yeah, so let me go ahead and draw an image of that on the next page. Right? Okay. And so basically the way that we define the angle, and we're using stick figure anatomy here, okay? The way that we define that angle is we drew kind of a line that kind of went down the middle of a person's body, right? Let me use a different color for this actually. And so we basically drew a line down the midpoint of a person's body, okay? And so if a person was standing up straight, their spine would line up exactly with this line, okay? But we're not doing a straight line, okay? We're not doing a person standing up straight. What we're saying is that this person is starting to tilt, okay? Right. Okay. Right, and so the angle theta that we're looking at is this one right here, right? Okay. But what we also have is we also have our base of support. So our base of support goes upwards like this, okay? Imagine all those lines are vertically upwards. Okay? And so because the midline and because this yellow line right here, they're parallel, right? And we say that the person's spine is kind of crossing both, right? Then what we can say is that this angle theta that we have here is exactly the same as this angle theta, which we use in the calculations. Mm-hmm. It's a little bit hard to visualize, I know, just because I drew everything kind of exaggerated just to make sure it's easy to see. But yeah, the two angles are equal, and the important thing is that this this thing goes down to where the midpoint is. Yeah. All right. Okay, and so that's that's kind of a default configuration, right? And so a person that's standing up normally, but there, like we said, there are things that you can do to make it easier for you to maintain balance, right? And so let's say that this person started to crouch down, right? And so let's say that he had the same base of support, and so he didn't make his legs longer, or he didn't put his legs any wider. Right? But if he starts to crouch down, right? And so let's say that he's maybe about to go play defense in basketball, right? Something that the Lakers don't seem to know how to do right now. Okay. If you compare where the center of mass is here, you can see it's much lower to the ground, right? And so because of this, let's say that this height here is only maybe 0.5 meters, okay, as opposed to 0.8, right? Okay. Then in order to topple, this person is going to have to rotate a lot more, right? Because this length here is small, right? And so you plug this into the calculations here. And so let's say that, instead of 0.8, you plug in 0.5, right? You'll see that you'll actually get an angle that's much bigger. And I don't have my calculator on me right now, but you should see that it's an angle bigger than 17.5 degrees. Okay. The opposite is true too. And so if you took a situation where you took your center of mass and you actually made it higher, it's going to make it a lot easier for you to lose your balance. Okay. And we can actually do an example that illustrates that. Okay. And so let's consider a situation where we have a person that's doing maybe an Olympic weightlifting move. Okay. And let's say that this person's lifting a 150 kilogram weight over their head. Okay. And let's say that this person, the mass of this person is 75 kilograms. And so this person is basically holding double his body weight above his head. Okay. Okay, so it might look something like that. Okay. And so above his head, we have 150 kilograms. From his body, we have 75 kilograms. Okay. And we want to do basically the same calculation that we did before. Okay. And so let's compute the amount that the person can rotate before they start to lose balance. Okay. And I need to give you some heights. Okay. And so let's say that the original center of mass is the same as before. And so let's say that this is 0.8 meters off the ground. And so that 75 kilograms is 80% of a meter up off the ground. And let's say that the height of the weight, this is going to be 2.4 meters off the ground. And just like before, let's say that this person has a base of support, which has a width of 0.5 meters. Right, so the dimensions of this person, the height and the width are the same as before, except now he's obviously lifting a huge weight above his head. The 2.4 meters is the height of the weight, right? And so above the person's body is being held 2.4 meters off the ground.
We just assume that the center of mass of the bar is acting directly.
Yeah, we're going to do that. Mm-hmm. Yeah, so basically, we're assuming that all the center of masses, in terms of the horizontal direction, they're all acting kind of in the midpoint, or starting to. Oh yeah, the 0.5 is the width of the base. And so it's the same as the previous problem. And so, you know, the 0.5 meters is basically the distance between his legs. Yeah, it's the width of the magical force field. Okay. And so, you know, before we start, right? If you're holding a big weight above your head, right? Intuitively, you would think that it wouldn't take that much to make you tip over, right? Because as soon as you tilt over to the side a little bit, then you know you have the intuition that the weight is just going to keep, you know, rotating until you fall over on your side. Okay. And so what we expect is that the angle that we compute should be a lot smaller than before. Okay, because you're you know, that indicates that you can't rotate nearly as much. Okay, any other questions on the problem setup? Okay, all right, and so let's do a center of mass calculation, right? And so because we have the addition of the weight of the head now, that's going to change the position of the overall center of mass. Right, and so if you remember from the beginning of the dynamics unit, you know, we had a formula for this, right? And so the location of the center of mass, which in this case, you know, we're only concerned with the height, right? And so the height of the center of mass off the ground is going to be the sum of the products of the mass of each of the object multiplied by their heights, okay, divided by the sum of all the masses. Right, so on the numerator, we're going to take the product of the mass and the distance, and on the denominator, we're just going to sum up all the masses. Okay. And so in the numerator, you know, we have two masses in the situation. First of all, we have the original body mass. Okay. And so our original body mass was 75 kilograms, and that one was 0.8 meters off the ground. To this, we're going to add the weight or the mass of the weight. And so that's 150 kilograms. And we're going to multiply it by its height off the ground, which is 2.4 meters. Okay. And on the denominator, we're going to just sum up all the masses. And so we have 75 kilograms plus 150 kilograms. And so that's going to cancel out the units of mass on the numerator, okay? And so if we run through this calculation, we'll see that the overall center of mass is 1.867 meters off the ground. And so to kind of draw this visually, I'm just going to draw the person again. Okay. If the original center of mass was right here, the new center of mass, you know, might be somewhere maybe over here. Okay. And so that combined center of mass, the height of this one is 1.867 meters. Okay. All right. But our base of support is the same. And so, you know, if the half distance in our base of support is 0.25 meters, okay. Question. So what does H represent again? It's just the center of mass at a height. It's the height of the combined center of mass. And so because this person's holding on to the weight, then the overall center of mass of the entire person plus weight system is 1.867 meters off the ground. Yeah. All right. And so if we draw a triangle again, right, where now the adjacent side is 1.867, okay, and we say that the angle that we can rotate is theta, right? And if we plug it in, if we plug it into our previous equation, let's say that we say that theta is equal to tan inverse of the opposite 0.25 meters. Now we're dividing it by the new center of mass location, which is 1.867 meters. Okay. And this is a much smaller number. And so the number that we get for this is 7.63 degrees. Okay. And so when you're holding a gigantic weight above your head, you can only rotate just a very tiny amount before you actually start to lose balance, which makes sense, right? And that kind of illustrates the fact that the higher your center of mass is, the easier it is for you to start to lose balance. And so one way you can think of this is that your body is working with a much smaller margin of error, right? And so if you could rotate 17 degrees in each direction, that gives your muscles some time to say that if your body is rotating, and then it's 17 degrees, that's when it starts to pull it back. With only a rotation of about 7.5 degrees, your muscles have to be under a lot more tension, right? Because as soon as you kind of deviate from that 7.5 degrees, which is not much at all, then your body has to be, okay, bring it back, right? And it has to even work even harder because now the center of mass is much higher, and the total amount of mass in the system is higher too, because you're holding that weight. Okay. Okay. So any questions on this?
So in a situation like this, would you be more likely to tip front to back? Or would you just because I feel like with something like a snatch like this, if you don't catch it right and it's too far forward or too far backward, the weight will go backward and you'll go forward, or vice versa.
Mm-hmm.
So obviously that's when you catch it, but when you stand up with it like this, would you say you would be more likely to tip back and forth or side to side?
You definitely you're more likely to lose balance front to back, because if your legs are kind of next to each other, then kind of the width of your base of support in that direction is much smaller. And so I don't have the exact numbers, but basically it would be half the length of your foot. And so instead of 0.25 meters right here, if we're considering the front to back direction, this would be replaced with whatever half the distance of your foot. So the distance between your toes and the middle of your foot, which might be only a few centimeters or something. So yeah, you're definitely much more likely to lose balance in that direction. Yeah. Mm-hmm. All right, question. So do abdominal and back muscles play any role in this as well in the different angles? Like if the person was more muscular, would they have more range on exiting the force field? So everything that we did so far is purely geometrical, and so we didn't do any force calculations at all, right? So we're only looking at the geometry. Having a stronger core, having stronger abdominal and back muscles will help you maintain, within this force field a lot more easily. Because if you don't have, strong core muscles and you start to tip over, right? And so the mechanism that your body uses to kind of bring yourself back is those core muscles. But if you don't have those core muscles available, then your body's not going to have enough, enough force to kind of bring yourself back to that position. But whether you're muscular or not, if your center of mass gets outside your base of support, you're going to start toppling them out. Yeah.
So would you say that your core muscles are almost like a factor of safety in this case, where it's no matter what, once you leave the base of support, it's pretty much guaranteed you're going to fall. Well, it is 100% guaranteed you're going to fall.
Yeah.
But your back and your core basically is preventing you from deviating outside of that once you start moving a little bit in one direction.
Exactly. Yeah. Yeah. That's a good way to think about it. There are different ways that you're once you start losing balance, there is ways for you to kind of bring yourself back. And we'll talk about that on Wednesday. Okay. But just to kind of give you a sneak preview, if you just kind of think you're standing normally and someone comes and kind of just shoves you really hard, right? And you start to topple backwards, kind of the natural thing to do is to start kind of swinging your arms, right? And so actually by swinging your arms, you're using different parts of your body to kind of counteract that rotation so that you can kind of bring yourself back forward. And so, you know, there are ways that you can do it. So it's not game over. So if you kind of, you know, go outside your base of support, you know, it's not that you're going to guarantee to fall all the time. You know, you're definitely going to start to rotate. You're going to start to fall unless you do something. But there are still things that your body can do, and having larger muscles for those things can help in those actions as well. But even those actions, there's only so much that you can do, you know, especially if you're kind of already way outside your base of support, then there's really not much you can do. All right, any other questions on this? Okay. All right. And so actually kind of building off Jacob's point, right? And so, you know, in the front to back direction, you know, naturally it's going to be a little bit harder for your body to kind of maintain balance. Right? Okay. And so in addition to your abdominal and back muscles, actually another muscle that helps a lot with this are your calf muscles. Okay. And so if we draw a free body diagram, okay, or if we draw kind of just a diagram, so let's say that this is a person's foot, okay, the most flat-footed person in the world, okay, right? And so we know that our calf muscles are responsible for plantar flexion, right? And so, you know, they act kind of along the Achilles tendon in the back, and they basically pull this way, okay? And so that's our FM, that's our force from the muscle, okay? And so by doing that, it's going to try to force the foot to go this way, right? And so it's going to try to do plantar flexion. But because, you know, your foot's resting on the ground, right? That FM is going to be counteracted by an external force from the outside, which is going to act basically at your toes, right? And so if you stand up right now and you kind of flex your calves, you'll feel kind of a lot of the contact happen in your toes, or kind of right at the, right at the balls of your feet, okay? Right, so this would be Fn right here, okay? And so this external force Fn, of course, this is going to be a large contributor towards, you know, keeping your balance in that front to back direction, okay? Okay. And this is a task that's really well suited for your calf muscles, right? And so your calf muscles, just by design, just by being at the lower extremities, you know, we talked about the muscles in your lower extremities are generally bigger and stronger than your upper extremity muscles, right? And your calf is no exception, okay? And so your calf muscles are, you know, fairly strong, and they also have a pretty decent lever arm with respect to the heel, okay? Okay. And in fact, you know, scientists have looked at, you know, lots of different people, and they've basically quantified how much torque the calf muscles can produce around the ankle, okay? And on average, the amount of torque or the average moment that the calf can produce is about 162 Newton meters, okay? Okay. And so basically whenever you start to fall forward, right? And so, what's basically preventing you from falling forward, a big part of that is your calf muscles, because you start to lean forward, then your calf muscles will flex. It's going to drive your foot into the ground. And the normal force from the ground is what helps you, prevents you from falling forward, okay? And the calf muscle is perfect for this, right? And so, you don't see very often that people are walking on the road and they just randomly fall forward, right? It's because a lot of times it's their calf muscles, in addition to their core, that kind of helps keep them upright. Okay. But what you don't see often is you often don't see people going around doing handstands, right? Because when you're doing a handstand, instead of your big calf muscles, instead what you have are your wrist flexor muscles. Okay, and your wrist flexor muscles are not designed for this at all. And so I'll draw it out on the next page and kind of give you some numbers to kind of illustrate how poorly designed the wrists are for maintaining balance. Okay. All right. Any questions on this? Okay. And so when doing handstand, okay. And so your wrist flexors are going to be the ones that kind of prevent kind of forward tilt. Okay. And so if we draw kind of a person's hands, okay, and let's say that he's doing a handstand. So let's say that this is the person's hand, and it looks like a cat's paw, but it's okay. Okay. And so just like the calf, the wrist flexors are going to act on kind of the inside part of your forearm, right? And so that's going to want to bring your wrist forward, okay? And that's going to cause a normal force on the ground as well. Okay. Right. And so when you're doing a handstand, your wrists are kind of performing that same role. Okay. The problem with this is that your wrist flexors are not nearly as strong as your calves. Okay. Okay. In addition to that, their lever arm, or basically the attachment distance between your wrist flexors and the joint, is a lot smaller. Okay. Okay. And because of these two factors, we can quantify, or I should say, scientists have quantified, through laboratory experiments, how much torque the wrist flexors can produce. Okay, and it was found that the wrist flexors can only produce 10 Newton meters of torque. Okay. And so obviously, that's way smaller than the calf muscles, right? And so because this torque is a lot smaller, people are much more likely to fall forward when they're doing a handstand, right? And so, this is, and there's a lot of reasons why people can't do a handstand. So the textbook will say, this is the primary reason people can't do a handstand. I can think of a lot of other reasons why people can't do a handstand. But this is definitely one of the big reasons where, even if you do have the athletic ability, or if you have or in most cases is if you have the drunk friends to help get you in that position where you can do a handstand, most of us can't maintain it just because we don't have the strength in our arms to help maintain balance. Okay. And so what's going to happen is that even if you get into that position, then you're just going to tilt forward because your wrist can't produce enough torque to kind of keep your balance. And so if you can do a handstand, it's a pretty impressive feat of athletic strength, because that means, first of all, you have the athletic ability to get there, and you have the strength in your arm to kind of maintain balance, which is not trivial. Yeah. Can I do a handstand? I definitely cannot. No. I only tried when I was drunk one time, but yeah. I mean, nothing bad happened. I just fell, but not an experience that you won't want to go through usually. All right. Any questions on this? Yeah.
So how chimps can use their feet the way that we use our hands too? So is this part of the reason why they're not suited to walk on two legs? Because the fact that they can move their feet, they have an opposable thumb there. So they need to find motor control, which means that they can't produce as much torque in the joint at their ankle joint as we can. So is that the reason why they can't walk on 2 feet for long distances?
It might be. I haven't really looked into it, all that much, but that does make a lot of sense. I think part of it's also their lifestyle is just kind of well suited to, not really being on the ground as much, but also being in the trees. And I think being able to walk on 4 legs kind of gives you a lot more stability when your usual terrain is a lot more uneven. But I think it's a combination of both those things, where I think because that's their lifestyle, then the muscles in their legs just never fully develop the way that humans did. All right. And so let's see. So we have about 6 more minutes. Okay, so I don't think I have enough time for the next example, but I can at least introduce it. I have one more kind of thing of trivia for you as well. Okay. And so if you've ever taken any kind of martial arts, maybe you're in martial arts right now, or if you did some growing up, what you'll notice is that a lot of the stances that you take in martial arts spread your feet in a certain direction. Okay? Okay. Right, because we've already talked about, in whichever direction that you spread your feet, whether it's kind of side to side or front to back, you're going to have much more stability in that direction. It's going to be much more difficult to lose balance. Okay? And so martial arts stances, they take advantage of this, right? And so if you look at kind of the logic kind of generally behind martial arts stances, then generally what they'll tell you is that the direction, or generally the logic is the direction that you spread your feet in is the direction that they are most likely to expect some blows from, okay? Okay. Because if you a lot of times martial arts, you're going to be fighting an opponent, right? And so that opponent is going to be throwing blows at you as well, right? Either punches or kicks, punches or shoves or kicks or whatever, right? And so for most martial arts stances, you want to stay on your feet most of the time. That's what gives you the biggest fighting chance. And so in order to help you maintain your balance, you want to spread your feet in the ways that, you think you're going to get struck. And so if you're expecting kind of a person to shove you kind of from the front, you want to spread your feet kind of such that you have one foot in front of the other, right? And so that gives you a wide base of support in that front to back direction. So if someone shoves you, then you can kind of maintain balance in that direction, right? But if you're expecting someone to kind of kick you from the side, then you want to spread your feet wide in that direction so that, when someone kicks you, you can kind of maintain balance in that direction as well, okay? And of course, the stances shift, as a fight goes along, but, that's kind of generally part of the logic of fighting stances, in addition to, putting yourself in a position to do strikes yourself, okay? All right. Okay, and so let's see, 2 more minutes. All right, so I think I'll save the example for next time. And so, because I think if I start drawing it, then we'll run out of time. And so we'll call class here, right? And so next time I have one more example to kind of drive this computations home, and then we'll talk about some methods that the body can do to help regain balance once they start to lose it. Okay. All right, so thank you guys for coming in today. I know it's the first class after the break, so I appreciate you guys coming out. Remember, so next week is going to be our final presentations, and so I'm going to put out a sign-up sheet for that, before class on Wednesday. Okay, so I'll send an email announcing it when I'm going to put the sign-up sheet out, and then another email to actually put it out. So keep an eye out for that, and discuss with your group whether you want to present on Monday or Wednesday. Okay, because we're going to need both class sessions in order to get to everyone. All right, so thank you everyone for tuning in today. Hope everyone has a good return from the break. We have 2 more weeks of class, and then then it'll be the end of the semester. So have a great day, everyone, and I'll see you on Wednesday. Yeah, yeah, and then after that, it'll just be final presentations.
The balance thing is interesting, especially like with the snatch example.
Mm-hmm.
Because the reason that a lot of people snatch that way is because you have to take the bars over your head in one movement.
Yeah. Mm-hmm.
And like people used to snatch like a split stance,
Mm-hmm.
like a clean and jerk.
Yeah.
So like they used to do it that way. But I think the reason why they do it this way now is because you can squat so much lower
Mm-hmm.
using a traditional squat stance.
That's true.
So
That's
it's
true.
like it's interesting because it's like a trade-off between balance and max weight.
Mm-hmm.
Because like if you catch it, then you're good.
Mm-hmm.
But like with a split stance, you can't get nearly as low, so you're not going to be able to put as much weight over your head.
That's true. That's
And then
true.
with the clean and jerk, now there's also like, I would say more people do the split stance, right? So like they throw their feet like super, super wide and
Mhm.
far apart. But now there's also people who will like throw the weight up and squat underneath it to like
Wow.
meet it overhead, right?
Crazy.
So like you can also jerk a lot more that way too, because all you have to do is push it up a little bit.
Mhm.
And then you can get super low by squatting all the way to the ground to catch it, as opposed to like the split stance where you're splitting apart and you can only get so low before you have to meet the bar overhead.
Mhm.
So I think it's interesting, just like the way athletics are evolving and stuff like that.
Oh yeah,
And
there's
and training methods and stuff.
yeah, and there's yeah, lots of interesting trade-offs that you don't like think about a lot. It's like you see it on TV and it's like, oh, that person's just lifting a heavy weight. But there's a lot of strategy and a lot of trade-offs that they have to think about. It depends on the person's body type too, and how well they keep balance. So
Definitely.
Yeah.
Yeah, I was thinking about doing Olympic weightlifting for the final project, but then I was like, it's so much more biomechanically complicated than powerlifting is. Plus, I'm more passionate about powerlifting because like that's my hobby, so I feel like I know a little more already.
that makes sense.
But I think biomechanically speaking, like weightlifting is the much more interesting topic.
Oh yeah.
Because there's such a mixture between like strength and technique where it's like body position matters so much in terms of like whether or not you're going to make the lift.
Mhm.
And with powerlifting, like there's a lot more wiggle room. Like even if your form is not perfect, like you still could make it. Whereas like with weightlifting, it's like you're probably not going to get it. So
That's true. That's true.
yeah. Alrighty, Professor. I'll
Alright.
see you in the next class.
Yep. I'll see
You
you.
want me to close this up?
Yeah, that'd be great.
We're gonna have to present as well.
No presentation. So next week, so we have an activity this week,
Mhm.
and then next week will be like miscellaneous week. So I have a lot of like smaller handouts that I've developed over the years, and I'll let you guys pick on which ones you want to see. So I have like handouts on how to do like thermal simulations in ANSYS, handouts on fluid simulations, how to do like an anisotropic material. I think I have one on fatigue testing too. For 410, actually, too, I have some extra ones that I've developed for my grad class this year on things like optimization, things like buckling analysis too. And so I'll let you guys pick. And so what you want to see.
It's like a final activity, correct?
Yeah,
Okay.
yeah. So one more activity this week, and then next week will be just, whatever you guys want to see.
Okay. And so for the final, is it like almost similar to the midterm?
It is.
basically?
It is.
Okay,
yeah.
cool. I was expecting like, it should be more harder, or is it the same? as the
It's
midterm?
very similar, except you're doing it on your own geometry.
Yeah, it's more of our own.
Yeah. That was my goal this semester, because in the past when I've taught this class, this is the first time I've done the midterm project. And so by the time we get to the final project, it's like kind of way too overwhelming at once, especially because this part of the semester is really, I know it's really busy for you guys.
Yeah.
And so I want to do the midterm project, which is most of the requirements of the final project, so that when you get to the final project, it's like, oh, I've done this before. It's just with a different geometry.
Oh, okay. Yeah, makes sense. Yeah, because I was like, it's too easy.
It shouldn't feel that bad. And that was my goal.
Oh, okay.
Because I didn't want, because end of the semester always crazy for everyone.
Yeah,
So
it
I
is.
wanted, and 410 is an elective. And so I want it to be kind of a positive experience. So
Yeah.
and by this time it should be easier.
Yeah. And then I don't know if we're gonna do the turnitin.com for the answers. I'm just kind of
Yeah.
scared that it might be like really exact as my senior design, because the senior design, I literally just grabbed the answers.